If you try to calculate the movement of every single atom in a vibrating airplane wing, you will run out of computing power before the plane ever leaves the ground. Instead, engineers use a mathematical workaround known as lumping of parameters. This framework for simplifying structural chaos comes directly from Dr. Chandan Chattoraj's ME 503 curriculum. To build a working model, we look for just two opposing forces. First is inertia, the tendency of a mass to keep moving once it starts. Second is restoration, the force pulling that mass back to a neutral position. Every vibration analysis boils down to stripping away the visual noise of the physical object until only these two elements remain. Before we can assign numbers, we have to classify how our system behaves. We will map this out using a matrix, mapping out inertia and restoration. Looking at the inertia column, we define it by the path of motion. If the object translates in a straight line, we use standard mass, denoted by m in kilograms. If the object is spinning or pivoting, we use the mass moment of inertia, denoted by I. Over in the restoration column, the pull back to neutral typically comes from one of three sources: the elasticity of the material itself, the pull of gravity, or external field-based forces like magnetism. Identifying exactly which variables belong in these columns is the required first step. You cannot write an accurate equation until you map the physical behavior to these specific categories. Let's apply this to a continuous structure, like a heavy, flexible beam anchored firmly to a wall. Step 1 of lumping is to gather all the distributed weight of that beam and consolidate it into a single, dense point mass at the location where the movement is most pronounced. Next, we account for the beam's stiffness by replacing the structural connection with a massless spring and define its motion path along a single axis. We have completely discarded the physical appearance of the beam. What remains is a pure mathematical model containing only the necessary variables for calculation. With our variables defined, we need to determine the system's degrees of freedom. This is the absolute minimum number of coordinates required to pinpoint the exact location of the system at any given moment. This diagram shows a single particle on a flat plane. It requires two coordinates, x and y, meaning it has 2 degrees of freedom. Move that same particle into 3-dimensional space, and you now need an x, y, and z coordinate, giving it 3 degrees of freedom. So if we place 2 completely independent particles in that same 3D space, how many coordinates do we need? We simply double the requirement to 6 degrees of freedom. But watch what happens to the math if we connect those 2 particles with a rigid rod, restricting them like a diatomic molecule. Because their distance is now locked, the coordinates must satisfy a constraint equation defined by the distance formula. Since we can always use that formula to solve for one of the coordinates, the system drops to 5 degrees of freedom. Every physical constraint you add in the real world directly subtracts a variable in the mathematical world. Establishing your degrees of freedom dictates your workflow. If a system is restricted to a single degree of freedom, you only need to write a single equation of motion to solve it. By taking our isolated mass m and our elastic restoring force k, we can combine them into the standard linear equation, mx double dot plus kx equals 0. Let's review exactly what we've covered with this summary graphic. We differentiate inertia by translational mass versus rotational mass moment, and we track our degrees of freedom based on spatial dimensions. And most importantly, remember the core calculation rule. Total degrees of freedom always equals the number of unconstrained coordinates minus the number of constraint equations. Mastering parameter lumping and degrees of freedom provides the logical framework needed to convert chaotic physical structures into precise, solvable engineering equations.